Hello everyone, I am Dr. Nishanth working as postdoctoral fellow under guidance of Professor Krishnan Balasubramanian at IIT Madras, India. So happy to meet you all at IEEE Sensors Virtual Conference. I am going to present my poster presentation titled Phase Shift Based Level Sensing using two wave modes T01 and F11 on a thin waveguide. Level sensing is critical in many of the process industries. In many of the process industries, level sensing is critical in many of the process industries. Most of the level sensors, ultrasonic level sensors, are based on microwave-based sensors and not guided wave-based sensors. And very few researchers have reported guided wave-based level sensing using thin waveguide sensors. So here we are reporting a waveguide sensor which is capable of generating all three wave modes simultaneously using a single shear transducer. So when a single shear transducer attached to a small thin metal waveguide, which is a 1 mm stainless steel in this work, and attached to the surface of a piezoelectric shear crystal at 45 degrees, it is capable of generating three fundamental wave modes: longitudinal, torsional, and flexural wave modes. And the cylindrical waveguide with a flat end can be used as a level sensor, which has been reported briefly by Rilbert's book. So what we are going to use here is the flat region is going to act as my sensor. So I am going to track two different wave modes, torsional and flexural wave mode for level sensing by tracking the change in time of flight of these two wave modes. When we have continued our level sensing measurements at each level of fluid immersion, you can clearly see the phase shift in torsional wave modes and the phase shift in flexural wave modes. The phase shift in torsional wave modes is mainly due to the mass loading of the surrounding medium, where the wave is unable to propagate further, so it is getting slower and slower. So the change in time of flight is mostly related to the mass loading of the surrounding fluid in torsional wave mode. Whereas in the flexural wave mode, the change in amplitude and the drop in amplitude and the change in time of flight is mostly related to the leakage of this wave mode to the surrounding medium. So we calculated the change in time of flight of both torsional wave modes and the flexural wave modes at different levels of immersion. You can see as the fluid level crosses the flat region, the torsional wave mode time of flight shift remains constant, whereas the time of flight shift of flexural wave mode is much more dominant till the complete immersion length, which proves that the torsional wave mode time of flight shift is only applicable wherever the flat region has been involved, whereas the torsional wave mode time of flight shift is much more involved wherever the flat region is involved. Whereas in the flexural wave mode, the time of flight is completely reporting at each level of fluid immersion. We are also tracking the change in amplitude of all three wave modes and found out that flexural wave mode amplitude is much more dominant at these levels of immersion. We have done multiple trials, and we have, from the multiple trial repeatability, we have found a good repeatability to these sensors, and the maximum error was found to be less than 2.5% of the total readings. We hope this multiple wave mode approach will be of interest to many industries, which will solve the industry problem in many of the process industry measurements, where one wave mode can be used for temperature measurement and the other two wave modes can be used for level measurement. Thank you.